All right, that's time. I'm feeling stretchy today. If you can't tell, bit tired. You're welcome to if you'd like as well. So today we're doing a review of the entire class thus far for the midterm. One thing I want to say is the midterm is probably going to be easier than you expect. Not to say that you shouldn't study or anything like that, but try to not stress about it. The point of it is not to punish you; it's to reward you for learning, right? Something like that, some cheesy shit. Also, homework 4 is out now. A couple things about homework 4. So it's doing autoencoders and GANs. One thing about that is that it will take much longer to train these models. So start earlier rather than later, because training the model will be the thing that will probably take the longest. You'll have to do hyperparameter tuning, which means you'll have to run the model lots of times. And for example, mine, running on my laptop, took about 3 to 5 minutes to train it each time, which is unheard of for you guys because you've only done with very small models. It's still very short, actually, in the grand scheme of machine learning, but do prepare for that. Also, it should be pretty fun, and take a look at it soon, I think. All right, cool, done with that. Now, first up, I want to show you all of the topics that I think are important and how important they are. So first up is supervised learning, so I've categorized them. So under supervised learning, we have linear regression. You can't tell because there's no reference point, but this is like medium important. Then we have the perceptron, which is a little bit less important. Not so you shouldn't know it, but it's pretty easy, and it's essentially just a smaller version of something that is more important. Loss functions, again, medium important. You should understand how they work. Again, we're going to cover all of this today, but you should understand how they work and what the properties of a loss function are and why we have loss functions. Gradient descent is very important. And if there's any main takeaway I want you to have from this class, it's gradient descent, so that is definitely going to be on the exam. Computation graphs are actually not particularly important. They are more a tool for you. It is not something that is necessary for you to know how to do, but you need to know that it exists and that it is how a computer calculates the gradient. And you can use it as a tool if you want to. I've had you do a lot of that on the quizzes to help you practice doing derivatives with this method, but it's not actually important that you know necessarily how to do that or that you can do a derivative with it. All right, MLPs, very important. This is neural networks is essentially what this whole class is centered around, so you really do want to understand those. Likewise, backpropagation is right there with gradient descent as the most important thing in the class. Understanding that algorithm is understanding how we do machine learning, at least neural networks. Nonlinearities are medium important. You should know several things about them. We'll cover that today. And classification, a little bit less important, but you should understand the difference between regression and classification and how you can convert a model that does regression to a model that does classification. Under unsupervised learning, we now have clustering, just the general concept of clustering. Nothing specific. We haven't learned any models that do explicitly cluster data, so you don't need to know anything like that. But you should have an idea of what clustering means. You should also have an idea of how an autoencoder works. So autoencoder and GAN are going to be both on here at medium important. You should understand how they work, and you should understand what they do and why we want that. Then we have everything else that doesn't necessarily fall under either of these categories, but are important still. For example, convolutions. You should understand how to calculate the sizes of convolutions, the output sizes of convolutions. You've probably had a lot of practice with that on homework 3. That's an important thing to know, and what they do and how they work is also important. Overfitting, we have hinted at throughout this class a whole lot. I haven't really taken any time to explicitly talk about it, but in all of this, where we've learned about having a trained set and a test set and how the differences matter, this is something that is important to understanding machine learning. And I think through what we've said in all of this and what covers in this review, you guys should have a good understanding of overfitting. Cool? And lastly, hyperparameter searching is not particularly important to understand the mechanisms of necessarily. More or less, the entire idea is try hyperparameters, see how it performs, pick the best ones. There is Grid search and random search, I would like you to be able to like identify what those mean, but not in any way of like, write me a loop to do a grid search or anything like this. Nothing like that. Just understanding how they behave a little bit. And basis expansions are something that I really have not covered in the class thoroughly. We talked about it a little bit. That's where we have the x's and the x's squared, like all the features, we take the square of each feature, or we take the sine and cosine of those features and how it behaves differently. I don't think I'm going to ask any questions on this, but I might. So take a look at the quizzes. Again, the quizzes are going to be essentially harder versions of what the exam is going to be like. So take a look at them if you want some sense of what the questions will be like. Yeah?
Would it be too much trouble for you to post the quizzes?
To post the quizzes? I suppose I can. I haven't been posting them because I want people to come to class to do them. But yeah, I can post all the old quizzes. Remind me if I forget. All right, cool, thank you. All right. Now, let's go through every one of those topics now. This lecture is going to be, these slides are very long. I have 45 slides. So it may run a little bit long, and I'm going to be talking pretty quickly. That does not mean that you cannot ask questions. In fact, I really want you to ask questions, and now is basically your last chance to ask me these questions, unless you come to my office hours tomorrow. All right. So the schema for supervised learning is we have inputs, x, and we're going to call them x1, 2, up to whatever, xn I have here. And we're going to have a corresponding label for each one of those. If we're giving the data and the labels, that's supervised. We're told what the correct answer is. And in our paradigm is that we're going to take in these inputs, put them through some model, and get an output. And we would like that we would get from one of these particular x's to its corresponding label. That is the ideal, if it works correctly. And then we come up with the idea that we can tune these parameters of this model to perform a different function, and we can decide what those parameters should be based on our data, both the inputs and the outputs. Cool, so that's supervised learning. And here's a little bit of an example. It's the same one from earlier in the class. We have inputs 1, 5, 8, 2, 3, and we have outputs 3, 11, 17, 5, and 7. And we realize, as humans, being really good at math, that there is a particular function that would transform these x's into these y's, and we saw that it was 2x plus 1, which we all identify as a linear function. So then we thought, how could we make a model of this? Well, there's two different things that we could change in a linear model to give us a different linear function. And we want to then parameterize those variables that we can change. So we're taking this function, which is just mx plus b, right? And we're saying, oh, m and b, we can change those. So let's come up with a model that has those as parameters, and then learn what those parameters should be. So in the case of this question, we'd have a model be y equals wx plus b. We call it w because we think of them as weights instead of m, which is slope for some reason. And in this case, both of these are parameters that we update. And we learn later down the line that we can actually treat these not just as numbers, but as vectors or matrices. Crazy. But for now, we just say that it's some parameter. Cool. And then in this case, we see that to get that y equals 2x plus b, we set w to 2 and b to 1. Cool. And then if we do this and we find the particular ones, we call that linear regression, because we're regressing to some continuous output value. Cool. Cool. All right. And then we learned that this model that we've now created, if we generalize it to have multiple inputs, we can call a perceptron. So now we'll have 3 x's. They'll all be put into a single y with these weights along the edges. And this perceptron model right here is, we gotta add the bias, Can't forget the bias until we can. And this will give us a model that is the summation of all of the x's multiplied by their corresponding w's. And we also realized that this operation is exactly the same as x dot w, so it's a dot product, a matrix dot product, plus b. Cool. That's the perceptron. Oh no. I guess you know what we're doing next. So now we saw that when we take a real example, if we take real data that isn't manufactured to give us an exact model, something like this, there are a lot of lines that we could argue are a line of best fit. We could make the argument that this is, we can make the argument that this is, look, it's going through more points. And we make the argument that this is, right? And there's no real way to say which one of these is the best line, right? There's none that fit perfectly. And so we came up with this idea of a loss function. So a loss function is just our definition of the model performing poorly. So we take its output and the real output, and we say, how well is our model doing? If we have high loss, that means it's doing poorly. So we want to minimize loss. We call that an objective function in optimization. So we want to minimize loss, but there are some constraints on how we could actually define a loss function. We can call it whatever we want, but there are a few things that we need to have for this to actually function. One, the minimal loss should be the line of best fit by our own definition. So if there is a best fit to our data, we want the lowest loss to correspond with that model. Two, the loss has to be defined at all points. So that means that at no point do we want to divide by 0 or do anything that would give us an undefined answer. Three, the loss function needs to be differentiable, which we've talked about on length why we would want something like that, but now you can see, of course we want that. We want to be able to calculate the gradient. Cool. And this is an example of a loss function that does not work. This is just the sum of differences. And the reason that this doesn't work is because if we wanted to minimize this, right, we see that our actual output is that y in green, and y prime is our model's output. If we wanted to minimize this, we would just increase y prime as much as possible. And we see that if we take that summation, we would end up getting a really, really low loss. So that doesn't work, which is why we add the square or the absolute value to our loss function for MAE and MSE. Cool. Next, we talked about gradient descent, which is, again, like I said, basically the most important part of this class. We realized that if we were to look at the loss function, like if we were to plot it out, right, as some surface, right, where the dependent variables are the different parameters, then we realize that we've taken Calc 3, and we know that if we look at some particular point, the gradient at that point is the direction of steepest ascent. So the gradient is the direction of steepest ascent, which is this top arrow. And then we also know that the negative of the gradient is the direction of steepest descent. So if we take a sufficiently small step in either one of those directions, we'll go as much up as possible or as much down as possible. And that up or down is our loss increasing or decreasing. And of course, since we've defined that we want a minimal loss, decreasing the loss is good. I know that we've covered all this, but repetition helps, I've heard. And then we realized that to calculate the gradient, we need to find the derivative of our loss function, right? If we're finding the gradient of loss with respect to w, which is all of our parameters, or all of our weights in this case, then we would find the derivative of the loss with respect to every one of them individually, and we would get a vector of all of those derivatives, and that is the gradient. It is that direction that we should update the parameters if we want to increase loss as much as possible, or we could subtract it to decrease loss as much as possible. And this is a very beautiful and simple idea that gives us the following, which is the formula for gradient descent, which is just that w, every time it updates, we will subtract the gradient of loss with respect to w. And if we take a sufficiently small step in this direction, we will guarantee that we will decrease loss, which is just a beautiful thing. And we can think of this if we want to iterate over every one of the w's, and we can think of it like in multidimensional even, that we're just updating them with respect to that particular weight. Cool. And the note there is that we need to take a sufficiently small step, so we actually are going to end up adding a hyperparameter, which we all know as learning rate. Yay. Cool. Computation graphs, a little reminder on them, right? So if we have a function like this, right, then our computation graph is going to be this entire function drawn out operation by operation. So we can think first like inner to outer. We do the addition of x plus 4, then we do the square, then we add 1, and then we take that to the power of 8. Cool. So that is that function. That should be acceptable for everyone. And then we label the outputs of each of those operations, a, b, c, and y in this case, because y is the actual output. And then when we ask the question, how can we find the derivative from y with respect to x? And what we realize is that this actually allows us to visually do the chain rule. We can take the path from y to x, and every one of those edges that we go backwards through is one partial derivative that we would take to get our chain rule. So in this case, do this. The first step is y to c, and then c to b, and b to a, and then a to x. Cool. So we realize all computation graphs are is a way for us to be able to visually do the chain rule. Wonderful. This becomes immediately useful to us because we can draw our model as a computation graph. This, for example, is just our perceptron with 2 inputs and 2 weights. And if we were to add on the loss function, it would just look something like this. We'd subtract that from y, we'd square it, and that'd be our loss. And if we go to take the derivative, we would just look along this path and we calculate it. And we see that it's pretty easy to see that when we're trying to calculate this gradient, we can find each of these derivatives very simply. We take the derivative on each of these steps and multiply them together, and we end up getting our derivative. Wonderful. So that, again, is the entire point of this. And then computation graphs, we come to learn, are exactly how the computer ends up calculating these. So it's very useful to understand if you're trying to think about how to do an AutoGrad program. We also decide that, okay, this is great, but this also sucks to making Google Slides, so why don't we use a different notation? And in this case, we can see that, if we were to think of this as, so we can see that this multiplication, right, this model that we just had a second ago, we can also write as just x dot w plus b, right? That matrix notation, that matrix multiplication notation we've been using. In this case, we'd have 2 vectors like this. And this model, we can then just say, is a single dot product. And since we already know the derivative of that entire operation, when we go to take the partial derivatives along this, we already know the derivative, so it's fine. And this sort of gets at the idea of modularization that we are going to see in PyTorch a lot, or you have already seen in PyTorch a lot. Yeah?
Clarify, is it x dot w or x dot w transpose?
So x dot w is a perfectly good way to write it. I took the transpose out of it because I think it confused more people than it helped. This is equivalent to that, except this is easier for you guys to write. Like, if you were to just take your code and take input dot weights, this is correct. So that's why I use this notation instead. They are equivalent, though. But yeah, cool. So now we have that. We realize that, okay, we have sort of multiple inputs now, which we've seen. But we can also have multiple outputs. So in this case, if we were to have some number of inputs and some number of outputs, I have D inputs and C outputs. If we were to have a single layer, that would mean that we would need one weight matrix of shape DC, because it's changing from shape D to shape C. Hopefully that's settled in with people by this point, that that's how that works. In that case, that would also mean that the number of parameters in that would be D times C. So we can start thinking about the number of parameters in a model. That will become more important later, not so much for this exam, but it's something we can consider, how many parameters our model has. Nice. We also learned that, okay, we have our perceptron now, and that's great, and people were really excited when it came out. We can do everything now. We can learn. And then it took only a very simple example of XOR, which we have here, to show that it is actually impossible for it to classify this. It can't separate these different groups, because no line can separate these different groups. It's not linearly separable. And our model is only linear. Right? And there is a way, though, that we can deal with this. Right? We have a linear model, and it can't solve nonlinear problems. Let's have a nonlinear problem. First, we're going to think, okay, so maybe the perceptron's not strong enough, right? Let's try making a bigger model, right? So this is before we have the idea of nonlinearities. I know you already know, but this is something they tried first. Okay, let's have multiple layers, right? Maybe this is more powerful. And in a way, it can learn different things differently, but it is fundamentally the same. So we'd see that we put this in, and now we have multiple weight matrix multiplications that are happening. But what we realize is that although we're doing that, we realize that if we do 2 affine operations consecutively, so there's 2 weight matrix multiplications or 2 affine operations, we would see that that is equivalent, theoretically, to doing a single different affine operation, meaning that our model is still linear. But if we were to add another function in between these 2 that is nonlinear, this property would not hold, which means that if we were to have some nonlinear function sigmoid, then we would see that this is not equivalent to some other affine operation, not necessarily at least, operation here. And this allows us now to say that our model has more computational power. Cool. And as a note here, this may be a question, yeah?
Just wanted to make sure you can still do XOR without
So he's asking to make sure, because I did say this before, that we can do XOR without a nonlinearity. The answer is we cannot. So I saw before that if we use a basis expansion, we can do that. With the basis expansion, we can solve a problem like XOR. The problem is that our basis expansion, for example, the polynomial expansion that we use to talk about that, which is where we take x and x squared, is doing a nonlinear operation. It's squaring all of these inputs. So as long as we are doing some nonlinear operation, we can increase this to be able to learn nonlinear things. Yes?
Can't you do multi-layer and one node for like each true value and then another node for ANDing each of those true values? I think you can do multi-layer without nonlinearity for it.
You definitely cannot, but
Can't you do one neuron for one true value in XOR, and then in second layer you have a neuron that is connected to all those true value and it's just basically doing AND between them, so basically 1, 1, 1, 1.
yeah. So the problem, I understand what you're trying to say. He's saying that we can essentially have one neuron that's able to detect whether or not we have one of the acceptable solutions, another neuron that detects one of those other solutions. The thing that you are missing here is that when we're doing that, when we're determining whether or not is an accepted solution, we are using a nonlinearity. We're using a threshold. Saying if it's above 0, then it's a 1. If it's below 0, it's a 0. You realize that those actual outputs are not 1s and 0s. They're either 2s or -1s or whatever, and that actually doesn't work. Good thinking, though. I used what I said earlier in the, yeah. So no, we cannot. It's a very well-known theoretical result that we cannot. Cool. And we realize also that if we're going to add a nonlinearity into our thing, right, that's expanding into our computation graph, we would like that we could have a differentiable nonlinearity, or we need a differentiable nonlinearity, but we would prefer that it's very easy to calculate that derivative, or very fast to. Again, with machine learning in general, and you'll really feel this in the next homework, speed is important. And if we have a very slow network, we can't do much. We can't train it, we can't get any good results. We need a fast network to some degree. So you'll maybe come to appreciate that these derivatives are very easy soon. So we had first sigmoid, which we all know and love. The little squiggly guy is compressing it between 0 and 1 with a little in-between squiggle right here. And we saw that its derivative is just 1 minus sigmoid times sigmoid, or sigmoid of the input, sorry. So that means that we just can look at its output and then multiply them together, 1 minus it, cool. So that's very nice. We also had tan h, which very similarly is a little squiggle, but now it goes between -1 and 1. And again, its derivative is very simple. It's 1 minus tan h of the input squared. So again, very simple derivative. And then most simple of all, we have ReLU, which is just a max between 0 and x. And it looks like that. And because it's like that, its derivative is very simple. It is only 0 if the input is below 0, and it is 1 otherwise. And as you really should have the question of, isn't that just a linear function, a piecewise linear function? It is, but fun fact, a piecewise linear function is a nonlinear function. Names can be deceptive. And you could also ask, Cooper, isn't there a nonlinear, or isn't there a discontinuity or a non-differentiable point at 0? We just define it one way or the other. We just say, okay, in this case I say 0 gives us a derivative of 1, which is not actually a smart idea. We would say that it's equal to 0. So we just make that decision, and that's fine. We ignore the fact that it has a discontinuity like that, or not discontinuity, whatever, and it's fine. It does work. So we also learned that sigmoid is not good for a couple reasons. It's better than other things, but it's not good in a couple other ways. One, for high magnitude inputs, it gives us a derivative of 0. or very close to 0, which is really bad for us. Because when we go to backpropagate through it, we are now reducing our gradient significantly. We're reducing the magnitude of our gradient significantly, which makes it slower to learn. Either we boost our learning rate a ton, or we end up not learning very quickly at all. Then we have 10H, which still has that problem, but in this case, it now passes through the origin, which sigmoid doesn't, and also can have negative outputs, which we like intuitively. We say negative outputs are good because we can keep some like proportionality between negative and positive. They're different kinds of numbers, and we can have both now. That's all well and good. But then, at the end of the day, ReLU is the best. It's not necessarily the best in all situations, but ReLU is the most used and is the fastest and generally has better performance. Again, as I said, it's an open question to know why. It seems way too simple. It seems like it shouldn't be able to learn nonlinear functions well, but it is. It seems like it's too simple and it doesn't have any negative numbers, but it's fine. So you're welcome to think about that. Maybe you can do your final project on that if you want. Anyway, these are our nonlinearities. These are the only ones that I'm going to ask you to know. There are plenty more that we could use, but these ones have very easy derivatives and have good properties that we like, except for the properties we don't like. Cool. So next we have this idea of classification. So we have now multiple outputs that we can have. Let's use it. So first up, we're going to have data that now, instead of having some output that is just a number, we're going to have a class. In this case, we're going to have yes or no. So this is the example of whether or not they pass the test or pass the class. And we see now that we just have binary labels, either yes or no. And we realize that what we would like to do is we'd like to be able to tell if some input is a yes or some input is a no. So we now have our model be able to separate them, right? So it's easy enough to see that we can make a line in between them. And then we say that everything to the right of it, right? So this is called binary classification in this particular case because we have binary outputs, binary labels, only yes or no. And we can also, the same way that we could learn a line that best fit, we can learn a line that best separates, right? And somehow we need to make the decision of how to take, this output right now is just some real number, right, or some floating number at each one of these points, and we want to turn that into a binary output, either yes or no. And the way that we do that is with a threshold. I got ahead of myself earlier. So I'll just say here. So the way that we threshold is we just say, okay, if it's above 0, if the output is above 0, is an example. We could have any bias we'd like, but we say the threshold is if it's above 0, then it's a yes, right? So everything where the output of the model is above 0 is a yes. Everything below is a no. And we set that threshold, and then we learn both our weights and that threshold, which is bias. Then we'd realize that we could get a line, and if we have our loss be whether or how correct it is or not correct, we actually find that it can separate anything that is separatable with its parameters. So that's very good. That's very nice. So we can learn to separate this, and we just use the nonlinearity of thresholding to say whether it's yes or no. Cool. All right. So now let's look at MNIST. So you all know MNIST from homework 3. I hope you're well acquainted now. Let's take a look at this model. So MNIST, handwritten digits. Don't forget that one. It's not technically important, but it's important to me that you know MNIST. It's one of my good friends. And we feed this through a model, and we get some outputs. So you might notice that these outputs that I've given you now sum up to 1. Right? So I'm saying that the output class of this is an 8, right? And I'm saying that that little gold one is the output for 8. I know that this isn't long enough, but I have limited space. And then we see that they add up to 1. The reason for this is that we are implicitly converting these, or not, we're kind of explicitly converting these into a probability that adds up to 1. The way that we do this is by using a softmax. So in homework 3, when you saw that we were using a softmax, I made a little comment about it. This is why we're doing it. So it converts it from numbers that could be like 1,000, 500, -50, and convert them all into the range of 0 to 1, and such that they sum up to 1. And in that way, we can treat them like probabilities. In that way, now when we have a label for our data, in this case, we have that this is an 8, we can think what should be the correct probabilities that it produces for this to be a correct label. And what we say is that it should output 1. Right, it's 100% chance it's an 8, we know it is, and it's 0% on everything else. And then having this label and this prediction, we can now produce our loss. In this case, this is just mean absolute error, or actually it's just absolute error. So we just subtract them and take that absolute value, and we see that we have different losses for each of them. Cool. So this is how we would do a multi-task classification and how we would get our loss from that. And then, like before, we just backpropagate off this loss, and we're dandy. Cool. So, so now we have some nonlinearities, right? We'd like to be able to add them to our computation graph. It's a little bit, Frankenstein together, sorry about that, but here we are, we're on nonlinearities now again. So we'd like to add the nonlinearities into our computation graph and see what that does. So we have our dot product like before, and we're going to say the output of that is 01. That's the notation I used in the homework 2. And then we're going to feed it through the nonlinearity and get A1. Right? And we're going to continue this through dot products and activations. And we realize that we have this really repeated structure. So this is our first sort of cheat, is that we realize there's a repeated structure going on here, and we'd like to condense that notation. Right? So to be able to condense the notation, we need to understand what the derivative of this operation is. So this would be one of the things that we would like to say is like one layer, essentially. Right? And so we can look at what it is. So this is the sigmoid. I'm actually using sigma, or sigmoid, which is the little squiggle, right, which you've used. And when we take the derivative of this, we see that the derivative of this is exactly equal to x transpose dot 1 minus a, which is the output of this layer, times a, which you should all be well acquainted with from homework 2. Right? And then what we do is we say, okay, we know now the derivative of this, and like I said before, if we know the derivative of something, we can use it as an operation on our computation graph. So we're going to say that this entire operation is now just going to be f. We're going to say this is f. I decided to use f instead of fc. I think it's better. So f. Now we see that we can say the same operation is now f of xw. And if we take the derivative of that with respect to w, we get the same exact answer, right? So it's the same operation, but now we have a little bit of a condensed notation. So this is our first idea, is that each layer is repeated, and if we know the derivative of a particular layer, that derivative is only dependent on the input, the weights, and the output of that particular layer. So we can just calculate the derivative of these iteratively, right? And we also notice the fact that we are using the output of this in each calculation, and that means that if we wanted to recalculate the output of something, or if we want to calculate the derivative of some later layer, we would have to recalculate the output of that layer, and having to do that over and over and over again is wasteful. So that's another thing that we notice. Cool. So let's draw a model that looks like this. So there's a multi-layer perceptron with the nonlinearities. We now have them just written as f. All right. So this would be 2-layer, and now we have this, which is our new output. Still using the sigmoid notation, not using f. And we realize we can take the derivative of this with respect to w1. All right. So now we have to backpropagate through this one layer. All right. So if we wanted to take the output of this, which is a2, with respect to w1, which is our first weight layer, we would do the exact same thing. Again, we have our chain rule, right? So we have dA2 to dA1, right? And that is exactly the same as taking the derivative of our f with respect to the input. That's f with respect to x. Yeah?
When you write f for A2, wouldn't that add sigmoid to the whole thing? Because you are doing w2f.
Yeah?
Then dot.
Okay, true. So technically with the way that I wrote the computation graph, because I have the f including a sigmoid, I should have a dot product there instead of an f because I'm not including a sigmoid in the final bit. Let's just say that we're not including it. I think I made the same error the first time that showed, but that's okay. I did update the slides, but I missed that. Cool. So then we see that this derivative is just going to be 2 terms. So the first term, a2 with respect to a1, is the same as our df with respect to input, which is going to be this, right? And I'm including now that 1 minus A2, which shouldn't be there based on what this model is written, but since I'm using F, so imagine there's another sigmoid outside of it all, and then this would be correct. So in this case, it would be that, and then dot product with this, right? So this would be, so you can see that this is with respect to the input, and we take the W2, and then with respect to the weight, we take the input, right? So we just take the opposite term when we're taking the derivative. It's like a multiplication. Cool, and then both of these will have the 1 minus the output times the output term in them because of the sigmoid. Cool. So now our idea too is that if we were to store each of these outputs, right? Yeah.
The T is just transpose, right?
Yeah, T, the T on the top is transpose. This is important for like implementations and to be very correct about the math. I'm not going to hold you to knowing or producing anything that has the correct dimensions on the exam because I think that's a hassle. You guys have practiced it a lot, and it's an important skill to know if you want to do machine learning. But I think it is something that is stressful, and I think it's a bit much. But yes, those T's are there to make the dimensions correct. Yeah.
So order also doesn't matter in the exam?
I don't think there will be any questions that will depend like that. Yeah. You'll see. You'll see. I'll see. All right. Cool. So we realized that because there's a lot of terms that we would have calculated if we went through our network calculating them, in our derivative, we can, in fact, memorize them as we go through to be able to use them when we calculate our derivative. And that was our idea of our backpropagation algorithm. So we now have another layer, right? And now we're getting to the idea of, well, we have many layers. We have to do this in a general way, right? So you know that if we're taking this with respect to W2, it's the same thing that we had before, right? This is the same thing that we had in the last slide, just like upping the numbers by 1. And then if we were to do it now with respect to W1, so these are both terms that we'll need to calculate the derivative, we'll see that it gets something like this. So we take the first step, and then we take the next step, and then we go to the weights, right? But we realize that there is repeated terms in these derivatives. That's not good. Repeated calculation, we hate that. So we want to somehow not do these calculations. And that's what we're going to do. So what we're going to do is we're going to remember those derivatives that we calculated, sort of, as we go, so that we don't have to repeat these. So similarly to how we're keeping track of the calculations that we did in the forward pass, where we calculate the output of our model, we save those A's. Now in the backwards pass, we also keep track of the derivatives that we've already calculated, so we don't need to recalculate them. We can actually be a bit more clever about it, though, because if we were to iteratively calculate the derivative with respect to each weight, we only have one term that is shared between each of the individuals. So we can just memorize one term as we go. So if we were to have the next term here, we'd see that it would repeat. So if we had dA3 with respect to dW1, if we imagine there's another layer in front, we'd see that it would share both dA3, dA2, and dA2, dA1. So now it would share two terms, and each time it only grows by 1, so we can just keep track of that term. It's only multiplying one extra thing. Yeah?
This term that you're referring to now, is that essentially just the dW in the backpropagation loop?
The dW. So the term I'm talking about now, where we're keeping like a running total of the derivative of loss with respect to the output of the current layer, is the d loss, I called it, or d out. I called it d out, I think, anytime I talked about it. It can be whatever you want to call it. It is essentially just keeping track of what the running derivative is from loss, or the output in this case, to the output of your current layer. So you're just keeping track of that derivative as you go, and we use that derivative to then calculate the derivative to our current weights. Yeah?
Quick question about this. If we were to find the derivative of some weight, we would just do all this, but we also have to multiply it by the derivative of the loss in terms of the...
Yeah, exactly. So if we were to have a loss function on top of this, then the first running term in all of that, so the first term in every single one of these would be d loss dA3. So that is a good thing for you to be able to have the intuition of, which is, if we have a single extra bit of chain that everything is now taking the derivative from, they'd all be multiplied by that one derivative. So that it's essentially you can use that intuition to extrapolate to this, which is good. Anyway, this all brings us to the algorithm proper. which is first we're going to do the forward pass, which is going through the layers forward, and then setting the output to just be that layer's operation, which we call f, of that layer's w, and that layer's input, which is the previous layer's output. Which we can see like this: if we have this layer, and we can say that A0 is x, right? Then our first iteration would take f of A0 and W1, and it would give us A1. And that's exactly how the model is working. So you go through each time, but now what we're doing is we're remembering each of these A's. So we're caching them in the homework. Here we just say that this variable is equal to it. Cool. And then once we go through this whole model, and we can calculate our, we can also calculate our prediction and then our loss and all of this, but we just say the output of our model. We don't really care what happens down there. Then we want to go backwards because we want to calculate each derivative. And we're only going to do one loop backwards. We're not going to recalculate it for every single one because that would be slow. So we're going to say that we want to calculate first the DL. This is the D loss or D output of whatever, like the end thing, with respect to the output of the current layer. All right? So initially, like we said before, like in the previous example, it would be like D loss, DA3 we could set. Right? And in this case, we would take this as this term times this term. So this is just the derivative. So this is, again, not entirely, I think actually this is proper. This is proper how you would actually write it, which is this is the derivative, the 1 minus AI. AI is the derivative through the sigmoid. And then we have the derivative from the loss to the previous layer, and then times W transpose. So this is essentially just saying we are taking the derivative up until the previous layer, then we're doing our one more step, and the extra terms besides the DL, DAI plus 1 are that extra step of derivative. It's not as beautiful as just having to multiply by a derivative term, but I wanted to be proper on here so you could see it. Yeah?
So the previous layer is I plus 1?
Yes. Or it'd be the next layer, but I've been calling it previous because we're backpropagating. Yeah.
In that case, do we, when do we put in the derivative of the loss, to initialize it?
Yeah, so it would just be before we run this loop. We would say, we would just define, we would just state what D loss DAL is. We would just say, we know what that is because it's the derivative of our loss function, and we would have it. Yeah. So that's exactly what we did on the homework. I don't know, I assume a good amount of people did get this. We first calculate that first step because we know it. Yeah. Cool. All right, and then we can also find, at each one of these steps, we can find the derivative of now the loss, or the output of our model. We could replace AL with loss, and all of this would be still correct. We can say that the derivative of our loss with respect to W is just going to be that term that we just had, the DAL, DAI, right, which is the derivative of our loss with respect to the output of that layer, and then just the derivative of the output of that layer with respect to our weights. So it's just that one extra step, and that extra step is just AI transpose dot that derivative. We could write it as times DAI DWI, but I'm writing it again properly here in the way that it is done in homework 2. Cool. Yeah?
What is the first DAL and DA?
The what?
So the first layer.
The first layer?
What's the D? So you see how we use the previous layer.
Yeah.
DAL, DAI plus 1.
Mm-hmm.
So it's like the first one, so where you don't have the previous.
Yeah, so that's pretty much exactly the same question. So he's asking, each time I'm calling DAL, DAI, I'm using DAL, DAI plus 1. So what is the initial state of that? And the initial state of that is exactly the derivative of loss with respect to, I know I'm using AL here, but we could easily replace it with L, just loss. Right? It would be the derivative of loss with respect to the output of our final layer. So there's that one first step, and that will be our first term. In the case of this exact situation, our first term would be our DAL, DAL minus 1. So we'd calculate that outside the loop, and then we'd use it. Or the other way around. Or yeah, no, actually that's fine. Yeah, like I said. Yeah.
So why would you use, in some spots you use multiplication, some spots you use dot product? What situations, why do we use multiplication versus dot product?
Yeah, so the dot product is a matrix multiplication which is changing the shapes of the inputs. When we take the derivative of an operation that is changing the inputs, or changing the shapes, we will change the shapes, you could think. They end up being reciprocated that way. When we're taking an element-wise operation, like our sigmoid is applying the same operation to every single element. So if we feed in something with some shape into our sigmoid, we get something out that has the exact same shape. So in the notation of the homework, the shape of OI and the shape of AI should be exactly the same, right? And because we're doing the operation on every single element totally independently from each other, when we take the derivative, we do the operation totally independent of each other. And the way we end up doing that is by multiplying them. So you'll see if you actually look at your homework 2, that this term, the 1 minus AI times AI, and the DAL over DAI plus 1 are the same shape. And that's because the difference between them, this is the same shape as DAI plus 1. They should be the same shape. And so you can just do a multiplication of them. It's not that we're multiplying because they're the same shape. We're multiplying them because we're doing an element-wise operation between them when we're first doing it. But one way to justify that we're doing it is that they're the same size. Yeah?
What is the element-wise operation? Would that be the sigmoid function?
Yeah, the sigmoid function is element-wise. So it's doing the same, that 1 over 1 plus e to the negative x is being done to every single feature of x. Yeah? Yeah. Are all activation functions element-wise? They don't need to be. You can imagine that I could call my activation function a matrix multiplication and then a sigmoid. I could say that's my activation function, and you're good. If you're asking if every nonlinear function is element-wise, that's also not the case. Yeah. Again, similarly, I know that feels like a weak argument, but I can say that matrix multiplication and then a sigmoid is a single function. I could just say that's my function. Right? It's perfectly fine to say that's a function, and it's a nonlinear function. It happens to be that we use element-wise functions because they're easy to take the derivative of. We're multiplying, not doing a dot product, and they happen to all be all the good ones we found. You could try coming up with a non-element-wise nonlinear function if you'd like, but it probably wouldn't be useful. Maybe it would. Who knows? Anyway, so after all of this, are there any other questions also? I think I saw a hand. Yeah?
For all the homeworks we were using batch, do you mind to talk about batch and backprop? I know it doesn't.
Yeah. So I know I've sort of just asked you all to accept the magic of it. But essentially, when we're having an input, we can have an input that is one-dimensional. So we say our x is just a vector. When we take a batch of something, if we're trying to take multiple inputs at once, is what a batch is. If we have a batch size of 8, means we're taking 8 inputs at once. The way to visualize what's happening, if you really want to, is we could say that we're just duplicating our network 8 times and feeding the input in through each of them. And now each one of the outputs corresponds to one of the inputs, so we'd have the same batch size in the output. The same logic applies to every operation we do. Right? We're essentially duplicating the operation however many times, in this case 8 times, doing it, and we'd have an output that has 8 of whatever the shape of the output is. So in all of this, what the magic is that we could include our batch and everything stays the same. Everything is still correct, which is very lovely. That's the justification. Does that feel okay?
Yeah,
or?
That's fine.
Okay.
I just didn't get the last part, that in what direction will you move? Because if you have bed size 8, you will have 8 gradients of everything, right? So 8 directions.
Yeah, so then we have the question of how to aggregate them. And the fun secret is we've been doing mean squared and mean absolute error. And that's exactly our answer, is we average the gradients and take them. So that's one thing where taking a batch is actually doing a different thing. So in the next homework and in this previous homework that you just did, in both cases we're going to have batches. And having batches actually changes the behavior of the learning. It is actually doing that. So that's why there is a difference between stochastic gradient descent, where we just take in one input at a time, and it's very jumpy. For every single input, there's a different optimal, so it's going in a whole bunch of directions. And if we're taking the entire data set at once, there'd only be one direction that we'd go. We'd go the same direction every time we take a step. So there is a difference when we take our batches. Cool? Cool. Anyone else? Again, this is like the most important part of the class, kind of, so you're welcome to ask questions. I'll take some time on this. Still practicing the awkward silence thing. All right, I'll say that. I'll say we're good there. So then our output is just the gradient, which is all of these derivative terms that we've learned along the way. Cool. Now we've calculated our derivative and our gradient, and then we can apply our gradient using stochastic gradient descent or whatever algorithm we want, and we're dandy. And now we are learning. Fun. And this is really how it does it under the hood when we're using something like PyTorch, where it automatically calculates it. This is pretty much exactly how it does it, which is pretty cool. Yeah?
I have a question going back to, I guess, like nonlinearities. Like, how come in the last layer you don't think that?
Oh, yeah. Okay, let's talk about that. Okay. Let's say that our target output is, like, let's do regression. Let's go back to regression, right? And we're doing scores in the class from 0 to 100, okay? And we just have a single output, right? What would happen if we're trying to predict the score from 0 to 100 if we had a sigmoid after the output? I'll let you think on it for a second, right? Yeah?
It would change all the numbers, and it would probably not be in the range of 1 to 100.
So in particular, we actually know what range it would be in with the sigmoid.
0 to 1.
It would be 0 to 1. So no matter what, our model would be outputting a 0 or a 1, like from 0 to 1, right? And in general, the data would probably have that the average is closer to like 50 to 70 at least. So probably what the model would learn is to just output 1 as much as possible. That's as close as you can get to being the correct answer. So because of that, we won't learn anything, actually. So fundamentally, that's the reason I didn't have you do the sigmoid at the end. You can say, OK, but what if my output is between 0 and 1? Then go ahead. Then it's fine. The real issue is just that, is the scale of the output. Having more sigmoids is actually worse. So every nonlinearity that you include is slowing down the training of the network and is, in general, losing information. The ReLU loses the least information, which is an argument to say that why it's the best one. But because of that, we don't want to include extra nonlinearities that we don't want. And if we had something that is outside the range of the output of our nonlinearity, it's a problem. Same as if we wanted negative outputs and we used a ReLU at the end. Same issue. We can't do that. Yeah. I feel good?
Yeah, that makes sense. Yeah.
Cool. All right, nice. All right, so we made it all the way through everything up until basically last lecture. And we started talking about unsupervised learning. I do want to take a bit of time to talk about it today. It's new, and it's also in the homework. But it's also very interesting, and it's its own section of the class, essentially, that we have condensed because I slowed down for backprop. So it's important to know. I'm also going to say that homework 4 is all about unsupervised learning. It is doing autoencoders. It's doing GANs. It will help you study, and it's also pretty interesting. If you prefer to study a different way, feel free, but the homework is going to be, I didn't mention this, the homework is going to be due on Friday instead of Tuesday. It would be ridiculous for me to say the homework's due the day after the midterm, but you still do have a homework, and it is still out now. Anyway, unsupervised learning. I actually made a slide to define it this time. So we'd imagine if we had our inputs, right, before we had our labels, and we're trying to fit our inputs to our labels. With unsupervised learning, we don't have any labels. And the question becomes, how can we do anything with that, right? So this is the case where we have unsupervised learning, is when we have data without any labels. That is very simple. We are not supervised because we're not told what the correct answer is to anything. We can say that maybe we're self-supervised, which you make the argument that autoencoders are, but that's not important. We don't cover self-supervision versus unsupervision. We say if we do not have labels, we are unsupervised. Cool. And you can imagine, like a simple example of what we might want to do is we could cluster things that feel the same together. Remember my good students versus gamers example. They're distinct in our mind. We can see that there are different clusters. And you can essentially think of this as us making our own classes and then fitting those to those classes. And we could also think of that as clustering, which is what it actually is. And then one advantage I didn't really talk about, but is an advantage definitely of unsupervised learning, is that there is much, 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 much more data that is unlabeled than there is labeled. Imagine all the data in the world, right? All the photos in the world, all the text on the internet, which is a real data set. then we could have much more data. So if we're able to use that data in some meaningful way, we can do very interesting things. This is what, for the sake of connecting it to the GPT-3, because I feel like they need to, GPT-3 uses just text from the internet. It doesn't give it labels. It doesn't tell it what it should predict next necessarily. You can see that in that situation, you can say, OK, it should predict the next letter as we go, but we actually do some more interesting unsupervised learning on it. Yeah?
Can we ever use supervised learning, and then after we run the data on our supervised learning model, we convert it into an unsupervised learning when we were out of the data?
I don't think at any point we could actually call it unsupervised if it has been trained on labeled data. You could call it like partially supervised or something if you'd like. It's much more common for us to go the other way around because we would like generally having some particular output is a task that we care about generally. We care about having a model that can output your score on the final. We don't care about a model that will just say nothing, right? And we could train it on this data and then say, we have some examples and we label it. It's an interesting idea. You could try it. There probably is some work on it. If you'd like to do it for your final project, it seems interesting enough. Yeah, but generally no. Cool. So principally what we're doing in unsupervised learning is we have some data, right, which I have colored in yellow and blue like you remember from Monday, as being different inputs that behave differently, that have different properties that are meaningful in some way, that I'm just telling you are. And what we're trying to do with unsupervised learning fundamentally is we are trying to separate these or distinguish these in some way automatically using a neural network. Not necessarily using a neural network, but in this class, using a neural network. Right? So essentially, we are trying to convert this data into something that is more interpretable, more usable. And we also realize that even when we're doing a supervised task, this is more or less what we're doing under the hood. So there are a bunch of different distributions that are all mixed together, and we're learning to separate them. We're learning to extract important patterns, important information. And so under the hood, we're doing the same thing, but now it is explicitly our goal to do this and to do it as well as possible. So this gives us our first very interesting, very cool model, which is an autoencoder. So we only have our inputs. Is there any task that we can create that feels a bit like a supervised task? So turn an unsupervised task into a supervised task, kind of. And what we come up with is that we can take our input as the input to our thing, fine. And then we also treat our input as the label. So now what the model needs to learn how to do is to reconstruct the input given the input. So in some way it needs to change it and then reconstruct it. The problem with this, we saw, is that it could just learn the identity function. It could just learn to take the input and return the input. That's totally possible, and with matrices, we just say that is the identity matrix. One's along the diagonal. All right? So to control this, we come up with the idea of compressing the data. So we explicitly require in the model that we are going to decrease the size of the representation of the data, and then we can increase it back to the original input size. And by doing this, we force the model to not be able to learn the identity function, at least in a simple way. And because of this, I draw like this sometimes. And because of this, we have at the center some lower dimensional encoding of features. Essentially at every layer we do, but at here it should be the most extracted, most important features, because just given those, it's able to fully recreate the image if it is able to do that. So these we think of as very good features, and where the name autoencoder comes from. We are automatically, using just the input, finding good encodings for that data set. It's a very simple and nice idea. And it is really as simple as just having a network that gets smaller and a network that gets bigger, and getting input and trying to get the same. We also saw that after we train it, right, so we have our encoder bit, which goes down to the size, and then a decoder bit, which goes back out, which you'll see in homework 4. We realized that after we train it, we could take just the encoder bit, and we freeze it, which means that we're not going to change its weights anymore. We're just saying that's our encoder. And then we can take that output, and feed it into another neural network to do some other task. So in the case of this, we use it to classify whether she's wearing glasses, how old she is, whatever we want. And because we've guaranteed in our own way that these features at this yellow point are good features, there's a good encoding of our input, then we should be able to use those features to do other tasks like classification. And this is the fourth idea, which is that these embeddings can be used for downstream tasks, which are other tasks using those embeddings, which is the main purpose of these autoencoders. We automatically get good encodings of our data. We also realize that we can take different augmentations of the input, so in this case black and white, and by taking the augmentation and forcing it to learn to get the unaugmented, we can learn particular things about our data, in this case something like structure. Yeah?
When you use the encoder to do other tasks, it's no longer unsupervised, right?
So this is where I said there's an ambiguity about it, where you could call this self-supervision if you'd like. We are creating our own labels, or our own inputs in this case, same deal. But really at its heart, this is still unsupervised. We're doing pre-processing and post-processing to do whatever, but it is still unsupervised. Yeah?
So when we pass those into another function, are they labels in that function, or are they the input?
So that'd be the input.
They'd be the input?
So you can imagine at here, right, at the middle layer, we would have that these are some very good representation of the input, right? They're very dense representing the input. And imagine that being fed into another network is very useful. Those are very useful things to know about the input. And because of that, we'd be able to do downstream tasks better.
Would that other network have labels?
It could. So in the case I gave you, yes. Then you could just do supervised learning on the rest of it.
Okay.
Yeah. As a sense, it's called transfer learning. Do some learning and then use that learning on a different task. Yeah. Cool. All right. And this is a useful application. We'd also see that after we do this, we end up with a network that is able to colorize photos. So we also have that, which is kind of neat. All right. Then we have this idea of generative models. So we can imagine that if we have something that takes in some input size and gives some output size, we could have it produce images of faces, for example, or whatever. And then we come up with this idea that we want to take noise as an input to get these things. And that's what we want to do. The reason that we want to do this is because fundamentally what we're doing is we're taking some distribution of data, and this is my first time that the time that I talked about it is the first time I talked about distributions, but everything is a distribution. I'm going to remind you. We take some distribution of data, and we try to transform it into some other distribution of data. In this case, a distribution of faces of whatever data we have, the input distribution. And we want to learn how to do that conversion with a neural network. And we are essentially just learning how to do that, and we'd like to learn how to do that, but it's not that easy. Right? So we're transforming distributions, and we're trying to identify distributions as well. Right? And that brings us to GANs, where we take this sort of setup. Yeah? So this is saying, imagine that we have data that is distributed the second way, right? That's just what the distribution of data looks like.
What does it mean for higher or lower?
So that would be essentially probability. So the height of it is the probability that that piece of data exists. This is one-dimensional data. They're saying each one of these points on the x-axis has some probability, which is the y-axis. So in the case of the bell curve, right? Some examples of that are IQ or whatever. The probability that you have this, the mean, is much higher than it is that you have one of the outliers. For the images, it's much more complicated. But essentially, you could say that the probability that this particular image is part of, is a face, right, has some distribution. And it has many, many, many variables. Right? Every single pixel is one of the variables in a different dimension. But it is still a distribution. Yeah. Anyway, yeah, this is a concept that takes a little while to swallow, but it is a good way to represent it for a few different reasons, most of which are outside the scope of the class, but still it's good to think about. And for us again, it's where we think about this now thing that can take some noise and turn into a face, right? Yeah?
Noise again is just what?
Is just some other distribution.
Okay.
So it's noise that we sample from a distribution. In this case, I have a bell curve. You imagine we'd have lots and lots and lots and lots of bell curves, and we'd sample from each of them, and that would give us some input, right? Yeah. Cool. So we'd say that this is going to be our generator, and likewise, we have a network that now determines whether something is real or fake, and we call that a discriminator. And we can use those two networks to learn together using the GAN training method. Because we have our generator, which is going to take in our noise. We have a discriminator, and we're going to take the outputs of our generator, feed them into the discriminator, and train the discriminator to output fake. And likewise, we're going to take real data, feed it into the discriminator, and train it to output real. Cool. So we would like it to learn, we'd like the discriminator to learn to output real only when it gets real data, and fake only when it gets fake data. This won't immediately be the case, but that's what we'd like to train it to do. And we can represent this just as a 1 or a 0, just to drive home. This is important for the homework, so I'll go over it a little bit more. But we also realize that the loss of this is non-obvious, right? In particular, the generator and discriminator must clearly have different losses because they are against each other. They are learning to do opposite things. In particular, yeah? So we just pass noise.
So the noise will create images?
Yes. It sounds like black magic, and it looks like black magic when it works, but this is fundamentally how GANs work. They take in random noise. The justification is on this previous slide, or not this one, fine, I'll just go forward. The previous slide where I showed that we're taking some distribution and transforming it to some other distribution. Right? That feels like a doable task, right? We're taking this distribution which has some amount of information, and we're trying to find some transformation function to a different distribution. That's what the generator is learning to do. And by using a discriminator, we're able to do it more effectively. Yeah?
If we were to pass in a white image and we get a face,
Mm-hmm.
another instance, if we pass in the same white image, are we guaranteed to have the same face?
So yes, so all these networks are always deterministic. So if we pass in something, we will get the same thing unless somehow we added randomness into our network, which is not a common thing to do. You could try it if you'd like. But yes, but after a little bit of training, we have no guarantee of that. So if we pass in, so the noise could be the same exact distributions, and we're sampling from those distributions, and because of that, the same distributions could produce wildly different faces, but it's not the case that the same input, the same sample itself, would produce a different thing. It would always produce the same thing. Yeah. Cool. Yeah. So by random, if you mean from these distributions, then yes. If you mean not from these distributions, then no guarantee of that at all. And in fact, it's very likely that it would produce nothing useful whatsoever. Yeah. He was asking if we feed in other noise that is not from our distributions, our Z distributions. And yeah, those would be useless. And then we saw that this was a loss function. The short version of this, because we're running a little bit low on time and I want to cover a little bit more, is essentially that the discriminator will have a very high loss if it is fooled by the generator, or if it says that real data is fake. And the generator will have a very low loss if it is fooling the discriminator. It will have a very high loss if it is not fooling the discriminator. It will actually have 0 loss if it's not fooling the discriminator, but that's considered very high for it. Yeah. Anyway, so those are all the terms, but really the takeaway here is that the generator and the discriminator have exactly negative loss functions from each other. And this is the loss function for actually the generator. I said last time there was a discriminator. This is actually the generator's loss function. But the discriminator would just be negative this. Yeah. Cool. So I'm going to kind of skip this, but the whole punchline is we want to find out the values of hyperparameters that are best. And we found out that a good way to do it is to just try a whole bunch and see how they perform. And this is grid search, where we're trying a whole bunch of different combinations. And we'd get something like this, where we're just looking at a whole bunch of different samples. And those samples give us some performance. And I showed these little distributions, which are not an accurate representation of what it would look like. these distributions that say, like, according to our learning rate, that would be our performance. And we see that when we do a grid search, we only select a small slice of all the samples according to the number of tests that we do, right? And we saw that if instead we do a random search, where we just randomly sample in the whole space, we cover the distribution of the learning rate much, much more. So because of this, there are situations where a random search is better, and there are, in fact, cases where a grid search is better. So you need to use your own intuition about which is better. I have you write your own hyperparameter search for the next homework, so give it some think. Anyway, and lastly, I think the last big topic that I want to talk about is convolutions. The main takeaway is we are doing the filter across the whole thing. I think people have gotten convolutions mostly there. We do the matrix multiplication on each one of those overlays that we do, and we get some output that goes in each one of the, this output represents each possible position of the kernel, and the dot product on those are the outputs. And to visualize it, we have this little animation, which I hope everyone likes. Nice, isn't it? Cool. But the main takeaway that is important for you guys to know for the exam is this equation, right? Which is that we are taking the input minus the kernel size divided by stride plus 1 in each one of the dimensions. They could have different ones. For something like the exam, I will probably have them be the same. I'll move the same stride in both directions, and we'll have the same kernel size in both dimensions, most likely. But that is the equation for that. We also have that we can add padding, which is just zeros along the outside of it. And we see that because it's on both sides, we have to multiply it by 2. That might be something that you get tested on. Who knows? And likewise, we get this, and we get the output. And there are situations where we need to pad to be able to get an output for other settings of our stride, our kernel size, and whatnot. And we also saw, very importantly, that in the case where we have a color image, for example, it would be a 32 by 32 by 3, which is an extra dimension. We want to do convolution there. We need to add that extra dimension to our convolution. We're still just doing a dot product over every possible position of it, but we'd add a depth to it. In this case, if we have 3 channels on the input and 3 channels on the out of the kernel, we would just end up having a 1-channel output because there's still only a 1-dimensional array of different positions. It doesn't go any deeper because it's the same depth as it. We also saw that if we were to take many of those filters, many of those convolutional filters, let's say they're all 3-channel and we have 10 of them, that now the output size of this, or the output shape of this, would be whatever shape we normally get from doing one of these convolutions, but we have 10 channels. So now the output of this would be 29 by 29 by 10. So we're adding an extra dimension by doing this. And we saw that these channels are all that determine the output of the depth of the output. Each one of these convolutions will change its size of the actual image by the kernel size, the stride, and the padding. But we determine the number of channels just based off of the input and output channels of each layer. So in this case, if we had 3 input channels, 10 output channels, and then we had 10 input channels, 5 output channels, then we would have 5 input channels in the next layer, 11 output channels, and the output of all of this, right, will be some size, but it'll have depth 11. We know that. It's totally independent of the other things. Likewise, the calculations of the actual size of the image itself, not the depth, is totally independent of the number of input channels. They're independent of each other when you're calculating them. That's something that I saw some confusion with on convolutions on the previous homework. The next homework still uses convolutions, so hopefully this will be helpful also on the exam. It's a very convenient thing to be able to test the convolution math, so it probably will be on there. All right, and here I also want to say that convolutions generally we use as feature extractors. So similarly to how before we were extracting features with the autoencoder, the convolutions, because they're able to get localization, right? They're able to look for certain shapes that are local in an area. They make very good feature extractors, so we generally want them to be at the front, but they do mess with the dimensions, so you need to be careful of it. And batches, likewise to everything else, do not matter. They will automatically be handled by all of these programs, by PyTorch. Justification, we can imagine we're just duplicating our network and feeding them all in. And just a reminder, we need to flatten the output of the convolution before